In this example, we want to apply our knowledge of calculus to help us sketch the graph of this function, y equals ln of 4 minus x squared. So the first thing we might want to consider is the domain of this function. Because for any logarithm, remember, it can only take positive values inside. So that would be the first thing, to make sure that our domain only considers values of x such that 4 minus x squared is greater than 0. And what would this be? Well, this would be the same as saying x squared is less than 4, which means that x would be between -2 and +2. Okay, so there we see our domain should only consider the values of x between -2 and 2. Okay. Now, what else should we consider? Well, maybe one thing we should consider is how the function behaves near those endpoints of the domain. For instance, I noticed that we're going to have a y-intercept. If I wanted to get our intercepts here, my y-intercept would be f of 0, which would be ln of 4. Okay, so we would have a y-intercept at ln of 4. Then the next question might be, when is this equal to 0? Well, remember that ln of 4 minus x squared will equal to 0 if the inside here is equal to 1, because we know that ln of 1 is equal to 0. And then solving this, we would have x equals, well, x squared equals to 3. And so x equals plus or minus the square root of 3. Okay, so those would be our x-intercepts. Ln of 4 would be our y-intercept. Now the next thing I might want to consider is how it's behaving as x gets close to 2 or as x gets close to -2. How is the function behaving near those endpoints of its domain? So let's suppose we're taking the limit as x approaches 2 from the left, because we know it can approach from the right. So, right, our domain is only between -2 and +2. So if it's approaching 2 here, it can only approach from the left. And if we're approaching from the left, then we know 4 minus x squared will approach 0 from the right, and so this will be equal to -infinity. I think something similar can be explained for what's going on as x approaches -2 from the right. Since here, if I'm approaching -2 from the right, 4 minus x squared will also approach 0 from the right. So that will also go to -infinity. So it appears that at -2 and +2, we actually have vertical asymptotes in the graph. Let's see, we have ln of 4 would be our y-intercept. We have the x-intercepts at radical 3. Negative radical 3. And one other thing we can check is to figure out on what intervals it's increasing or when it's decreasing. So when I take f prime here, for instance, we would have -2x over 4 minus x squared. Notice that this will be positive for x greater than 0. Or, sorry, for x less than 0. And actually here, because we can't consider x that are beyond -2. So this will be positive for x that are between -2 and 0. So we know it'll be increasing on that interval. And then it'll be negative for x that are between 0 and 2. So it'll be decreasing on that interval. We can go a step further and also find its concavity, which I think here we can probably guess will be negative. So it'll always be concave down, but let's just quickly do the second derivative. So the derivative of the numerator will be -2 times the denominator minus the derivative of the denominator will be -2x. I'll put plus 2x times the numerator, -2x, over the denominator squared. And let's see, this simplifies to -8 plus 2x squared, and then minus 4x squared. So I get -8 minus 2x squared. And so actually factoring out the -2 upstairs, perhaps it's easier to notice now that this will always be negative. So you got -2 times something that's positive divided by something that's positive. So that means it's always going to be concave down. So we've gathered quite a bit of information, and the final sketch would have to look something like this. Right, we know it's concave down, tends towards -infinity as it approaches to -2. Here we want to think of what changes now if I were to take the derivative of ln of the absolute value of x. In this case, I would probably want to consider two things. Because here the absolute value really doesn't change anything if x is positive. On the other hand, if x is negative, then it switches the sign to the opposite. So what we can do is consider each of these separately. In the case when x is greater than 0, then the derivative of ln of the absolute value of x is equal to the derivative of ln of x without the absolute values. And so this would just be 1 over x, like we know. On the other hand, if x is less than 0, then the derivative of ln of the absolute value of x is equal to the derivative of ln of negative x. So applying the chain rule here, we have 1 over negative x times the derivative of negative x, which is -1. But then these negatives cancel, leaving me with just positive 1 over x. So in either case, we see that the derivative of ln of the absolute value of x is equal to 1 over x for any x. Now this is important because now it gives us a function that has a larger domain. So notice that this ln, when I put the absolute value on the x, can take any positive number or any negative number as its input. The only value that's not allowed is x equal to 0. So that allows us to get a more general antiderivative formula for 1 over x. So notice that the antiderivative of 1 over x we can write as ln of the absolute value of x. And we need the opposite values there because, again, here we consider this the most general antiderivative because now this has the largest domain for this antiderivative. So let's practice using this formula a little bit. Suppose, for instance, I want to find the area of the region under the hyperbola xy equals 1 from x equals 1 to x equals 2. Well, this is really just the equation y equals 1 over x. So if we're going from 1 to 2, we're just looking for the area of that portion of the graph. So we'll integrate from 1 to 2, 1 over x. And this will just be ln of x evaluated from 1 to 2. So of course the area here would just be ln of 2 minus ln of 1. Since we know ln of 1 is equal to 0, this will just be ln of 2. How about the integral of x over x squared plus 1? Notice here I can substitute the denominator. So we'll start by letting u equal to x squared plus 1. So then the derivative would be a multiple of the x that we have in the numerator. So our integral then will have a 1/2 from the substitution. Then x dx becomes du, with the x squared plus 1 in the denominator as our u. So this integral transforms into 1/2 integral of 1 over u du, which we know that's just the ln of the absolute value of u. And then putting the u back in, we have 1/2 ln of the absolute value of x squared plus 1. One thing I notice is that because x squared plus 1 is always positive, it's actually not necessary to include the absolute values. However, one last thing I could do is then bring the 1/2 power in as a square root on the x squared plus 1. So you can actually go a little bit further and write this as ln of the square root of x squared plus 1. Here's another example. One thing I notice here is we're integrating from 1 to e, and we have ln of x over x in the integral. So the trick that we want to look out for is that when we have ln of x inside the integral, we can look for an x in the denominator to go with the substitution. Because now when I take u equal to ln x, the derivative will be 1 over x, which we have here in the integral. So that'll be the trick here, is to let u equal to ln x. And then du will equal to 1 over x dx. And so that takes care of the 1 over x dx that we have in the integral. So the ln of x here becomes u. 1 over x dx becomes du. And now what I'll also do is change my limits of integration. So when x equals 1, our u becomes ln of 1, which is really just 0. So our bottom limit becomes 0. And when x is e, well, we know that u equals ln of e, which is 1. So our upper limit becomes 1. And now we have a much simpler integral. Integral of u squared will be u squared over 2, evaluated from 0 to 1. And that will just be 1 squared over 2 minus 0 squared over 2, so just 1/2.